Good day everyone. I am tasked to present linear independence and basis and dimension. So I am Robert L. Olasco Jr., your presenter. So the prerequisite concepts you must have are real vectors, linear combinations, and spanning sets. So first, linear independence. The vectors v1, v2 until vk in a vector space V are said to be linearly dependent if there exist constants a sub 1, a sub 2 until a sub k not all 0 such that the summation of a sub j, v sub j from j is equal to 1 until k is equal to the sum of a sub 1, v sub 1, a sub 2, v sub 2 until a sub k, v sub k is equal to 0. Otherwise, the set of vectors are called linearly independent whenever the sum of a sub 1, v sub 1, a sub 2, v sub 2 until a sub k, v sub k is equal to 0, where a sub 1 is equal to a sub 2 is equal to a sub k equals to 0. To illustrate, let's have the following examples. First are the vectors v1, v2, and v3 in R4 linearly dependent or linearly independent. So we must form the dependency equation and its homogeneous system of equations. So first we have a sub 1 plus a sub 3, a sub 2 plus a sub 3 is equal to 0, a sub 1 plus a sub 2 plus a sub 3 is equal to 0, 2a1 plus 2a2 plus 3a3 is equal to 0. So the corresponding augmented matrix is being presented and its reduced row echelon form that you can always verify. So we have the trivial solution a sub 1 is equal to a sub 2 is equal to a sub 3 is equal to 0. So therefore the vectors are linearly independent. Example number 2 are the vectors v sub 1 is equal to t squared plus t plus 2, v sub 2 equals 2t squared plus t, and v sub 3 is equal to 3t squared plus t2 plus t. In p sub 2, the set of polynomials having a degree, the highest degree is 2, are the vectors linearly dependent or linearly independent. So we have the following homogeneous system. We have equation 1 being formed by the coefficients of the terms with variables t squared. Equation 2, a sub 1 plus a sub 2 plus 2a sub 3 is equal to 0 is being formed from the coefficients of the terms with variable t, and the equation 3, 2a sub 1 plus 2a sub 3 is equal to 0 are the constant terms. You can solve the system of equations. You will have equation A, that is twice equation 2 less equation 1. You will have C1 plus C3 is equal to 0. And as you can observe, equation 3 is equal to twice equation A. The system of the linear equations has infinitely many solutions. So there is a non-trivial solution. A solution, for example, can be a sub 1 is equal to 1, a sub 2 is equal to 1, and a sub 3 is equal to negative 1. So, you can have v sub 1 plus v sub 2 minus v sub 3 is equal to 0. The vectors are linearly dependent. Example number 3 is S equal to the set of vectors having the following elements. The first vector composed of 1, 2, 3. The second vector is 0, 1, 2. The third vector is 3, 0, negative 1. Is S a linearly independent set of vectors in R3? If S is equal to the set of vectors v sub 1 until v sub n in a r raised to n or r sub n, let A be the matrix whose columns or rows are the elements of S. Then S is linearly independent if and only if the determinant of A is not equal to 0. So, if we form the matrix from the set S of vectors, so you will have a 3 by 3 matrix. Since the determinant of A is equal to 2, we conclude that S is linearly independent. Example number 4. Let V is equal to R sub 3 and also V1, V2, V3, and V4 are given. So based from the given vectors, we find that V1 plus V2 plus 0 V3 is equal to V sub 4. Others also like V1 plus V2 plus 0 V3 minus V4 is equal to 0. V1 is equal to negative V2 minus 0 V3 plus V4. So you can observe that V1, V2, V3, and V4 are linearly dependent. If S is a set of vectors in a vector space V, then S is linearly dependent if and only if one of the vectors in S is a linear combination of all the other vectors in S.